Hi, and welcome back to a couple problems I'm going to be doing in real analysis. This one comes from a qualifying exam from the University of Michigan. So the problem is asking us to find a necessary and sufficient condition on some subset E of R, the real numbers, such that LQ functions on that subset E are contained in LP functions whenever we have this relationship between P and Q. We're going to exclude the case where Q can be equal to infinity, but I believe this statement is also true where Q can be allowed to be infinity as well. So let's remind ourselves very quickly what it means to be an LP or LQ function. So a function f is in LP on this E if the norm of f, the p norm of f, is finite. And for me, I'll be taking this p norm to just mean the integral over the absolute value of f to the p power with respect to the Lebesgue measure over E. And then we also take the fractional power 1 over p of that entire expression. So if that's finite, then our norm is finite and our f is in LP by definition. So maybe the first idea that we have is that E is small in some way. So if we restrict E down to a very, very small subset, or even just a measure zero set, then the statement is kind of trivially true. So our first idea might be that it's small. And we're dealing with Lebesgue integration in LP spaces. So kind of the natural thing to think is maybe mu of E, the Lebesgue measure of the set E, is finite. So if it's finite, then maybe we can find a way to prove that it's sufficient. Maybe you believe that already. But the fact that it's necessary is true too, and we'll show that shortly after. So let's take a look at the first method to proving sufficiency. So the first thing we have to do is we have to assume f is in LQ of E, and then we want to show, WTS want to show, that f is also in LP of E. And then since we took some arbitrary f, we know that that's how we show that sets are contained in one another. So this first hint that I've written for myself up here is kind of that we're going to split this p norm of f. So let's take a look at the p norm raised to the p power, which is what I've written here. So the p norm raised to the p power of f splits into these two integrals. And the first integral, you'll notice, is just where the absolute value of f is bounded above by 1. So because the absolute value of f is bounded above by 1, or raising it to the p power, those values are going to be getting smaller because p is greater than or equal to 1. So that integral is bounded above by the integral of 1 with respect to the Lebesgue measure over the set E. And the second integral, so I'll write that 1 there, and the second integral, which is the values of f which are larger than 1, this p, again, is greater than 1 or greater than or equal to 1. So these values are going to be getting larger. So that means that this integral here, we can replace the p with q, because as we assume in the beginning of the problem, p is strictly less than q. So this integral is less than or equal to the integral of the absolute value of f to the q power with respect to the Lebesgue measure over E. Okay, so we're almost done. All we need to recognize is that this first integral is just the measure of E, which we assumed was finite, and the second integral is the q norm raised to the q power. So both of these quantities are finite by assumption, which means that their sum is also finite, which means that the p norm of f raised to the p power is finite, and therefore f is in LP of E. So that's the first way to prove sufficiency. So we assumed our finiteness condition, and we were able to show that f indeed does lie in LP, so we have that containment. The second way to do it, which you might like if you're a fan of Holder's inequality, is to use kind of conjugacy pairs. So the conjugacy pairs that you'll use are q over p and q over q minus p. And the way to kind of see that is to look at this fraction here on these fractions here on the left, which is a little easier to see why this is true, and then we can rewrite it in the way on the right. So the way that people sometimes look at this is that you have your f norm, your p norm of f rather, and then you want to somehow rewrite that in terms of your q norm. But on the surface, Holder's inequality doesn't really say anything about this, right? Because it only really says something about the one norm, namely that the one norm, so the Holder's inequality, just to recall, says that the one norm of two functions, f and g, is bounded above by some p norm of f and the p conjugate norm of g. So if you pick your conjugate pairs nicely, maybe you could come up with a nice inequality. But here, it's not entirely clear how we would do that. But the reason I like this is because we know that really this p norm is just f to the p, well, the one norm of that, and then we have to worry about kind of this 1 over p power as well. So it's kind of just a clever way to rewrite it. And if you don't believe it, then really write it out with the integrals as well, and then it'll be maybe a little more clear. So the thing we can do is we can then use Holder's inequality on this function, f to the p, not f, and we can apply these conjugate pairs, q over p and q over q minus p. So we'll apply q over p to just f to the p, which means that by Holder's inequality, we will get, I believe it's just f, well, I guess maybe I can write it out with the integrals. We get f to the p to the q over p d mu, and then we get this kind of nasty fractionals on the outside, which is just q over p, and then on the very outside we have 1 over p. So you can see it kind of gets a little bit messy, but I think it's a little easier to look at once we reduce it. And then the other function we're applying it to is literally just the function 1. So we're just saying f to the p is really just f to the p times 1. That's fair. And then we really want the 1 to worry about this weird conjugate q minus p. Okay. So this thing on the left, you might already kind of see, is really just something very, very nice in disguise. Namely, these p's cancel out right here. These p's cancel out. So you get absolute value of f to the q d mu. And then on the outside, yeah, over here I wrote q over p, and that should just be p over q because we take the reciprocal of that. And on the outside, that's just going to be to the 1 over q times. So on the left, we're able to make this integral into the q norm. And on the right, well, if we write out this thing, it's just 1 to some power, which is just 1. And then d mu over e, and then we take that to the reciprocal of the q over q minus p, so it's q minus p over q. But this is just the q norm, as we said. And then on the right, we just have, it's just the measure of e to some power. But the measure of e is finite, so the power of it is finite. And f we already supposed was an LQ function, so it's a finite quantity times a finite quantity, which is, of course, finite. So this is kind of another way to do it using Holder's inequality, Holder's inequality. If you're partial of that as well and kind of playing with the conjugate pairs. And I think that this is a little bit more of an illustrative example for maybe harder problems as well, which is why I chose to show it. But this is definitely something that you could do. The first method of sufficiency is something you could do just by maybe just the day you learn LP functions. Okay, so then the last thing we have to do is prove that this condition is in fact necessary. So namely, if we stripped this assumption away, if we allowed E to have infinite measure, can we produce a function in LQ which is not in LP? And kind of the trick is to look at maybe a more a simpler case. So if we pick, P is 1 and Q is 2, then kind of a function that might not be in LP is 1 over x, right? Because if we look at the integral of 1 over x, 1 over x with respect to x, or you could just write the Lebesgue measure again. And again, we stripped E to have finite measures, so now it can have infinite measures. So let me just pick the set maybe 1 to infinity, right? And then this function we know does not converge. In fact, this integral is infinite because the harmonic series diverges, and that's our integral test. So on the other hand, when q is 2, 1 over x squared, well, this integral, the same integral over the same domain, 1 to infinity, in fact converges for the exact same reason. So you could say, I think it's called a p-test in calculus. So now we want to kind of generalize this notion to general P and Q. And the way to do that is really just to look at this 1 over x function and take the power of it that we want. So I think the power of it that we want is going to be the pth root of x, 1 over the pth root of x, right? Because then if we apply the p norm to it, so if we apply the p norm to it, we get back 1 over x dx over e all to the 1 over p. So this 1 over p on the outside doesn't matter because the inner quantity is going to be still infinity, just like we showed above. But the difference in the q case is that the q is still larger than p. So raising it to this power gives this integrand, the x in the denominator then has a power greater than 1, which again we know by kind of the integral and p-series test that this is going to be a convergent integral and is going to have a finite quantity. So in fact, this assumption of the finiteness of E is necessary as well.